Okay, hello, hello. So it gives me a lot of pleasure, and it's an honor to be standing here as McMaster's newest Music Cog faculty member. I'm super happy to be here with all these people and to be, introducing a speaker at NeuroMusic. So this is great. So our last invited speaker for today is Psyche Loui. Psyche is Associate Professor of Creativity and Creative Practice in the Department of Music and Director of the MIND, that's Music Imaging Neurodynamics Lab at Northeastern University. She got her undergrad at Duke in psychology and music and a PhD at UC Berkeley in psychology. Psyche studies the neuroscience of music perception and cognition, tackling questions such as what gives people the chills when they are moved by a piece of music? How does connectivity in the brain enable or disrupt music perception? And how can music be used to help those with neurological and psychiatric disorders? I've long admired Psyche's work in science. She's very versatile and has a very diverse set of interests and great studies in a lot of fields. So today we'll be hearing, I think, about her work with alternative scales. But she also has been doing work on using music for treatment of Alzheimer's and difference between jazz and classical musicians, et cetera, et cetera. So it's a pleasure to have you here. Thanks.
Thank you, John, for that kind introduction. It's really wonderful to be here and seeing so many familiar faces of friends and making some new friends. Yeah, it's been really fun. Thank you for having me and for cleaning up my coffee spill in the morning. Yes, so I'm running on this computer that has had coffee spilled on it earlier today. So we'll see how it goes, but there are multiple backups, so hopefully it'll be good. All right, so the title of my talk is Prediction, Reward Expectation, and Musical Anhedonia. Can we switch it to the video? Thanks. And I'm especially excited to be talking about this here at the LIVELab, which you get to experience, because I think one of the shared interests, research questions we have is how does music bring people together? And there's nothing as well built as the LIVELab in the world to be built to ask that question from the ground up. So I think that's really amazing to see how that's developed over the years. And over the past couple of years, my colleagues and I, including Pat Savage and Bronwyn Tarr and Tecumseh Fitch and a few others, got together and thought about this question and really thought about musicality, or the capacity of perceiving and producing music, as a biologically and culturally co-evolved system for social bonding, right? So the idea is that different musical features such as rhythm and groove, we've already heard a lot about that today, but also harmony and the fact that music has different discrete pitches and form different scales around the world might then tap into these basic neurobiological mechanisms or neurobiological substrates that then give rise to that shared social bonding experience of musicality as at a ultimate level. So that question of prediction and reward is really what I'd like to get at. And of course, what people predict and what people find rewarding is different for different people. And of course, understanding that is one of the goals of more applied music cognition research. I had a bit of a personal experience with this, and when I was in high school as a piano player and a violin player, and I used to volunteer in a nursing home and play piano for older adults, and I thought I was being so good. I was playing all this Beethoven sonata, and then someone threw something at me and said, "Hey, Psyche, how much do we have to pay you to lighten it up?" So apparently, there's not one size fits all. And there's no more people that really illustrate that phenomenon of not everything works, right? Not everything is rewarding when it comes to music. As this gentleman here, BW, he was our first case of specific musical anhedonia. And I had been quite interested in music and emotion for a while. And when a previous paper got published, BW heard about it and then got in touch with me saying that he does not enjoy music. He's never enjoyed music, and he doesn't understand why anyone would enjoy music. So he would say things like, we interviewed him at length, and he would say things like, well, I would go to a drugstore and the checkout line, and I would see teenagers who are bopping to music in their headphones, and I would wonder, why would you want to do that? And so, why do people do that? So I guess we've heard a lot about why people do that today. So sometimes it's these kind of curious lack of an association between prediction and reward system that we might have thought as fundamental to music that makes us question the norm, right? So I wanted to, in thinking about how we got to this point of proposing this theory of the evolutionary origin of music, if you will, I kind of went back in our files and I found this original version of the diagram that I just shown earlier, which was drawn up by Tecumseh Fitch. I love how it's like a back of a napkin kind of picture, but you can see that most of the structure is already there, right? So this ultimate function of music for enhancing social bonding, but then the specific mechanisms that include some rhythmic features and some pitch-based features that then tap into this neurobiological underpinning, including prediction and reward. So I think I'd mostly focus on how these musical features tap into this relationship between prediction and reward systems in the brain today. And just before I really launch into that, I just wanted to say how this idea of different musical features around the world tapping into the prediction and reward systems of the brain might be thought of as a quite general framework, but also a non-cultural specific and maybe even an anti-racist framework. So since that paper came out, unless you've been living under a rock, you're aware of the Black Lives Matter movement and how the world has kind of had a reckoning about racial justice. And this reckoning, it permeates every aspect of society, but also music theory is not an exception. So you might have come across Philip Ewell's really influential work on music theory's white racial frame, right? The idea that there exists a white racial frame in music theory that is structural and institutionalized, and then unless you really actively deframe and reframe this white racial frame, otherwise it's very hard to make positive anti-racist changes in music theory. And so you might not have read this yet because this is a forthcoming Target article in the Journal of Music Theory that specifically is by Jason Hughes, and specifically it talks about the use of the term tonality being inextricably entwined, entangled with white supremacist ideas, especially from Eurocentric historicism that created the modernist movement that thus continues to delegitimize non-white music within our institutions. And when we think about how, at least in the US, we teach music tonality, there's tonal harmony and there's post-tonal harmony. And tonal harmony is very much kind of still based on this 19th century white music framework. And so, so what is it that our field can do to really address this kind of stark picture, right? Is there something that music perception and cognition can do to look past that specific white racial frame of music theory? So I think that this predictive coding model of music is very exciting. So we already heard quite a lot about that from Peter earlier today. This idea that we have a predictive model of music and how it tends to go, and that's informed by what we've been exposed to in our environment. So after that paper, Who's It All came out, Pat Savage and Shinya Fuji and other colleagues wrote a response to this towards a cross-cultural framework for predictive coding in music, where they asked, well, shouldn't you also be looking at different kinds of music from different cultures? To which Who's It All replied, said yes, and we think that no matter what culture you come from, you are forming predictions from sounds in that environment, in the environment in which you are imbued. So I think that seems right to me, but what I'd like to think about is if we are really focusing on musicality, which is the capacity of humans to appreciate, perceive, produce music, why are we focusing on music that has been made? Why can't we be focusing on music that has not yet been made, but the capacity of making future music? So I've been spending a lot of time on this, right? So I'm going to start with these specific kinds of predictions that you might form in different musical features that might not be common and might not be well established in any musical system of any known culture. And so over the years, I've spent a lot of time thinking about musical scale, right? So musical scales are one form of predictions that you might form. And so the idea that you have discrete pitches that are arranged with predictable features, right? So the equal tempered Western musical scale is based on a 2-to-1 frequency ratio, right? So one octave that is a tone that is one octave above another tone is twice that frequency. And then within that 2-to-1 frequency ratio, you've got 12 logarithmically even divisions of that ratio. Right, so this is you've probably all heard it before, but this is equal tempered 12-tone chromatic scale. All right, and different musical scales around the world make use of different steps along that system. Right, so here is a very Western diatonic piece. It's composed by a French composer trying to sound Spanish. So that's a very Western sounding piece. Chinese pentatonic scale, for example, uses five steps along that 2-to-1 frequency ratio. So this is actually the same violinist, but from the scale structure, you can see that it sounds quite different. All right, so even if you've not heard that piece before, you're familiar with the instrument, but there's something about the way it's treading on specific pentatonic scale notes that makes it kind of signal a very Chinese kind of intent, right? So different musical cultures use different steps along the 2-to-1 frequency ratio, but all known musical scales that have been looked at use this 2-to-1 frequency ratio. And then Heinz Bohlen and John Pierce independently started to question why we have to be based on a 2-to-1 frequency ratio. Why can't it be based on a 3-to-1 frequency ratio? So they derived this new scale called the Bohlen-Pierce scale, where one tritive now, instead of one octave, is based on a 3-to-1 frequency ratio. And then within that 3-to-1 frequency ratio, we have 13 logarithmically even divisions of that frequency. All right, so it sounds like this. All right, so why 3-to-1 and why 13 logarithmically even divisions, you might ask? So it turns out that if you take certain pitches along that scale and you play them together, you start to approximate low integer ratios in frequency. So you can use that to build a new major chord. So you can have tone groups, right, that make chords together that sound relatively psychoacoustically consonant. So we can take 0, 6, and 10, where each of those numbers stands for n along this scale, and so it gives you one frequency, and then you can string 4 of these chords together, and now you have a chord progression, and it sounds like this. All right, and so we've done lots of different attempts to generate these melodies from this chord progression. Here we have some human-generated melodies written by our wonderful undergraduate student, Yiwen Zhang. So this is one of them. All right, so I heard someone say, oh, not bad. Right, so it's like, oh yeah, there's something, it's actually possible to make good music in a lab. Right, and it's also possible to make good music while having complete control of what went into the stimuli, right? And so because we can have complete control over these melodies, we can then also recompose certain melodies. And so here is an altered version of that melody. You hear that the ending is a little bit different. All right, so they're quite similar until you get to the ending. And the real difference is that there's separate manipulations of number of times each tone occurs, and the last chord is different, right? So considering this kind of 1-4-5-1 chord structure, the altered version of the melody does not tread on tones that would end on, that would be equivalent to the one chord. But otherwise, they're similar. Rhythmically, they're similar. In terms of kind of spectral entropy, they're quite similar. But what we can then do is we can manipulate the original versus altered to generate a prediction error, right? So a difference in prediction. And you can change that by manipulating how many times each person hears the different numbers of melodies, different numbers of times, right? So you can independently manipulate exposure and prediction error. And so in our set of studies, we had people listen to melodies in an exposure phase, a variable number of times, and then after that listening exposure phase, they had to make familiarity and liking ratings. So they had to listen to each melody afterwards. That was either original or altered, and they had to make ratings for how familiar they were and how much they liked them. And so what we saw was that the familiarity ratings were very clearly predicted by exposure, right? So as you increase the number of presentations, people say that they become more familiar with them. But then, and that familiarity rating drops off for altered melodies, but the altered melodies were still sensitive to the number of presentations. It turns out that liking ratings also showed an increase with number of presentations. So the more you heard that melody, the more you said you liked it, but then that difference is also significant. So you see both an effect of number of presentation and an effect of prediction error. So this was done in thousands of US participants. We also replicated this in folks from China, right, who were recruited based around Beijing, and they showed similar effects. Right? So both Chinese and US participants showed familiarity ratings and liking ratings that scaled with number of presentations and were decreased with prediction error. But the one group that did not show same relationship between prediction and reward was people with musical anhedonia, right? So the BWs of the world who score very low on the Barcelona Music Reward Questionnaire, turns out that they still said that they were familiar with the melodies, but it took them fewer repetitions before they said, I'm done with this, I don't like it anymore. And finally, we looked at functional MRI activity during the perception of these melodies that had been previously learned in the scanner, and we saw that there was more activity in the Heschel's gyrus during the perception of original melodies versus altered melodies. And furthermore, we saw that the functional connectivity between the Heschel's gyrus and the medial prefrontal cortex scaled with the number of presentations and also reduced with the prediction error, mirroring the effects of in the behavioral experiments. So there really does seem to be something about the way the auditory prediction system taps into the reward system that seems to be different in people with musical anhedonia, and it seems to be subserved by this functional connectivity between the auditory and reward systems. All right, so we wanted to get a little bit more into kind of note-by-note detail of how people form predictions for these kinds of melodies. And so this is some of the older work that I will kind of briefly use to motivate some of the newer work. We had also used machine to generate a lot of these melodies using finite state grammar structures. And so this is one of the melodies that is automatically generated. Right, so they're just tone sequences that follow a finite state grammar set of rules that was determined by the same chord progression that I'd shown you earlier. So they're not human composed melodies. But for those melodies, you could have people listen to them for a while, and then you can get note-by-note measure of how predictable they were. Right? And we can do this using a classic paradigm called the probe tone paradigm that has been around for a while, pioneered by Carol Kromhansel and colleagues, where you listen to a melody followed by a tone, and you just have to rate how much you expect that last tone, and how well that last tone fit with the preceding melody. And so what's been shown before using the Western scale is that, of course, if you play a melody in C major, the C gets rated as most highly expected and G most highly expected and so on, kind of mirroring Western tonal theory and also mirroring the statistics and frequencies and probabilities of music that you might hear in the Western scale. So we started asking, can you see this in the Bohlen-Pierre scale as well? And so we had this simple task where you're going to do this, all right? You hear a melody followed by a tone, and you just have to rate on a scale of 1 to 7 how well that last tone fits the melody. Okay. Okay, on the scale of 1 to 7, people are kind of unsure. 5, maybe 4. Okay, so we're kind of 4-ish and 5-ish. All right, so this is the profile of what you're about to be exposed to. This is what people rated before exposure, and this is what people rated after exposure, right? So you can see that there's a clear increase in correlation between the blue line and the red line, suggesting that people during the course of exposure had become familiar with the frequencies and probabilities of notes within that exposure set. So the more astute folks among you might say, well, what's with significantly above 0 pre-exposure rating? So did people come in with knowledge of the musical system to start with? And it turns out, no. We are such amazing statistical learners that just the trial itself, or just the fact that I gave you one melody and then asked you to make that rating, could actually influence those pre-exposure ratings. So what we could do was partial out the profile of the melody that was used to obtain the ratings. And when you did that, the pre-exposure correlation drops to 0, and the post-exposure correlation is still statistically significant and above 0, suggesting that you really didn't know anything about the musical system before you came in, but you were really willing to learn and absorbing those statistics in real time. All right, so all these studies were done using pure tones, but the earlier studies that I'd shown you were done using clarinet tones. And so why is that? Right? So it turns out that timbre plays a role in this. Right? So I'm just going to play you 2 instruments playing the same pitch, and I'd like you to guess which instruments made each pitch. Okay. Any guesses for what instruments played those? Yes. Close. Clarinet, also close, but no. The first one was the flute, and the second one was the pan flute. I was looking at Laurel being like, aren't you a flute player? All right, so it turns out, so they were clearly playing the same pitch, but there's something maybe, I've asked students, and they thought, well, the second one sounds more hollow. Right? What does it mean to sound hollow? Well, it turns out that if you take a slice of this spectrum and you look at it, and the 2 tones are playing, the 2 instruments are playing the same pitch, and so the fundamental frequency is the same across the 2 instruments. but the pan flute has more odd harmonics, whereas the Western flute has both odd and even harmonics. And so that's a result of the closed tube structure of the pan flute as opposed to the open tube structure of the Western flute. Given that the pan flute has energy at fundamental frequency, and then 3, and then 5, and then 7 times the fundamental frequency. Well, 3 to 5 to 7, where have we seen that before? So that is actually the core chord structure of the Bullen-Pierce scale. So there's something about the musical instruments or the timbre of the musical instrument, specifically the distribution of spectral energy across the frequency spectrum, that's going to give you knowledge about the musical system as it unfolds. Then the pan flute and other instruments that emphasize odd harmonics, like the clarinet, should be better at helping you learn the Bullen-Pierce scale. Should be more suitable instruments for playing the Bullen-Pierce scale. And if you go and become as nerdy as I am about microtonal systems, and you go hang out with like avant-garde composers, all 5 of them who write music in the Bullen-Pierce scale, it turns out they're all writing for the clarinet, and they're writing for the pan flute. They're not writing for the Western flute, sorry. And I think it's because there's something about their perception that they're using to hear out what makes a good instrument for the Bullen-Pierce scale. So we decided to test this formally by generating timbres with both odd and even harmonics. And so here, and we replicated this Bullen-Pierce scale probe tone paradigm that we looked at, and the dependent variable we were interested in was the correlation between the probe tone ratings and the exposure itself. So here we'll just play those for you again. Okay, so you have to rate that last tone on the scale of 1 to 7 as opposed to this condition. You know, they both sound quite weird, and not one sounds particularly better than the other, but it turns out that the people who were exposed to the odd harmonics condition learned better than the people who were exposed to the even harmonics condition. And this is true both for the general correlations and for partial correlations, suggesting that there's something about spectral distribution that's affecting your prediction of musical structure. And it's really exciting because I think there's been a lot of ink spilled over statistical learning and the idea that you're learning from sounds and conditional probabilities between different sounds to derive language and grammar maybe, but those studies have not really taken into account this important aspect of the spectrum of sound. And so what I'm saying here is that there's something about the spectral distribution of the pan flute sound that's giving you knowledge about Bullen-Pierce scale, much like maybe there's something about Western flute or other instruments around the world that have been giving you your knowledge of your musical system all along. And so, and so if that's the case, right, is it even limited to music, right? Could it not be the case that there are other sounds in the world, such as the speech sounds from your mother's voice, that might be cueing you towards the statistical structure of language and speech in your environment? All right, so I think it's been very exciting to think through these questions, and the idea that so we've done a few more studies, but what I will say is that even simple drum sets, so you've already seen a lot of examples of this, but even prediction and reward mapping over time, right, as you can tell from these groove stimuli from the SEN group that was already been mentioned earlier, we started to ask how individual differences in reward sensitivity might actually map onto the ability to perceive groove, which is of course another way in which folks have looked at prediction and reward. And so how do you identify people with musical anhedonia in the general population? So this is something that Nick Kathios, who's in my lab, has done. You sample a large continuum of people along the Barcelona Music Reward Questionnaire, which started out as a 5-factor questionnaire, but now it's a 6-factor questionnaire. And then you also control for individual differences in physical anhedonia scale, right? So to qualify as a musical anhedonic, you have to score low on the Barcelona Music Reward Questionnaire while not scoring low on the physical anhedonia scale. And so we had replicated the famous inverse U curve, which is the kind of the hero of the day so far. And so it turns out that even people with with musical anhedonia do show an inverse U curve in their pleasure ratings, and also a little bit in their wanting to move ratings, but they also show generally lower pleasure and wanting to move ratings compared to their matched controls. But then the apex, right, the apex of this inverse U curve actually depends on individual differences in music and reward. All right, so that's one way in which our lab and many other labs, it seems, is interested in the mapping of prediction and reward. But amazingly, right, so we can see that these predictions unfold over time, but you can also form predictions for single sounds, right? You'd think that, so gestures, for example, might inform those predictions. So here we have some work that was just presented in one of the posters. I'm going to play you 2 sounds. Right, and they're very similar, but the only thing that's different is the shape of the amplitude envelope between them. Right, so this first sound is more like a bing, which has a sharp attack time, and the second sound is more of a wing, which has a slightly less sharp attack time. And so what we did was we asked people how intentional are these different sounds, and it turns out that the intentionality ratings decreased with attack time. So the bing sound was perceived as more intentional than the wing sound. And so just suggesting that we might be bringing different kinds of predictions to bear even in our perception of single sounds. All right, so we went on to ask more about, so given that you can have certain predictions for single sounds, do you also form pleasure for single sounds? All right, so you might all have thought of different sounds that you might find to be pleasurable. Some of them maybe are musical sounds, but maybe even non-musical sounds. Can they be pleasurable? And do musical anhedonics also find those sounds to be not pleasurable, right? So answering this question about whether musical anhedonics also like non-musical sounds gets at the question of how specific is music anyway, right? And so you can think of some sounds that might be pleasing because of associations you might have made in your environment. So that might be a sound that's pleasing because it signals money, and money is pleasing, all right? But then you might also have some sounds that are relatively abstract. Right, so that doesn't really, I don't know why that played twice, but that doesn't really signal anything, right? It sounds like a fairly abstract sound, but yet people mostly find that to be pleasurable or pleasant. So what we did was we used the same way of identifying musical anhedonics and matched controls in the general population, and we asked them to rate pleasing or displeasing on the scale of -3 to +3 individual single sounds, some of which were environmental sounds and some of which were synthesized sounds. And it turns out that the musical anhedonics were not statistically significantly different from their matched controls for environmental pleasant sounds, but they were statistically significantly different from controls in synthesized or generated sounds. So there's something about using the cues from the environment that seems to be helping musical anhedonics make ratings for pleasure. And by the way, this is only specific to the pleasure ratings. For the displeasure ratings, everybody hates the terrible sounds the same amount, which is also not surprising. But it does bear mentioning that pleasure and displeasure might be different mechanisms, not just opposite ends of the same spectrum. And so then we went back to look at people's ratings, right? We asked, without any sound cues, right? We recruited our musical anhedonics and controls back into the lab a month later, and we asked, how much do you like slot machines? Without actually showing them, playing them the sound of slot machines. And it turns out that people's ratings for the pleasantness of slot machines and babies laughing and other pleasant things correlated quite well with their ratings for those sounds. But that correlation was higher for musical anhedonics than for controls, suggesting that musical anhedonics who weren't deriving pleasure from auditory predictions in the first place were more prone to be using cues from their environment to form these associations. So it's really exciting to think about how this is a way of getting at how your life has been all along, right? So when you think about BW, right, the original OG musical anhedonic, perfectly well-functioning person, perfectly, normal and good verbal skills and all that. So how did they get to be here? It turns out you're using so many additional cues from the environment. And so maybe it's those additional cues that we want to understand a little bit more. Right, and so how do we form associations from sounds is a question that our collaborator Lisa Margulis, whom a lot of you know, has really been interested in for a while. Right, so they have this really interesting paradigm where they play you a piece of music. Right, you might not have heard that piece of music before, and then they just ask you, what story do you imagine when you're hearing this piece of music? And it turns out that if there's some gestures that are a little bit fast and tends to cue certain stories, and people are surprisingly consistent in what stories they narrate and imagine when they're hearing pieces of music, even music that they had not heard before. And so what that previous study had done was use Chinese music and Western music and played them to people in China and in the US. And so we wanted to know whether Bohlen-Pierre scale music, which is presumably equally unfamiliar for both groups of people, might also elicit these same kinds of imagined content. Right, so we had people from Boston and from Beijing listen to excerpts of music that were created in the Bohlen-Pierre scale, and then write stories about what they imagined for these pieces of music. And so here I'm showing you the word cloud of the stories that Boston folks and Beijing folks wrote for the same piece of music. And you can see that they're generally using different words, but there is some similarity between them and kind of the maybe semantic content of those pieces of music. However, if you look at the semantic similarity using natural language processing tools for the narratives that were generated for each of those 8 excerpts of Bohlen-Pierre scale music, we saw that the Boston folks generated stories that were more similar to each other, whereas the Beijing folks generated stories that were more similar to each other. And so there was a significant difference within culture versus between culture, which replicates their previous result. And furthermore, then we wanted to ask, well, what about the people who don't imagine the consensus story, right? What if I am one of those weird people that heard a piece of music that for everyone else sounded like cowboys, and I heard breezes in the trees? So what we wanted to do was define this semantic space as an individual difference measure. And so for every consensus narrative, we made an additional measure to capture how close each person's story is relative to that consensus narrative. And so you can do this separately for people from Boston relative to each other's stories and people from Beijing relative to each other's stories. And it turns out that there's higher consensus across the Bostonian folks than there were for Beijing folks. This is without any differences in narrative engagement, right? So both groups thought that the tasks were similarly interesting, but the Beijing folks were less likely to converge on a consensus narrative than the Boston folks. And furthermore, among the Bostonian folks, this measure of semantic conventionality, right, which is the similarity of their narratives, was negatively predicted by the absorption subscale of the EBMRQ, extended BMRQ. So people who reported being more absorbed by music actually wrote less culturally conventional, maybe even more creative stories. Whereas people from Beijing, we saw a negative prediction between gold MSI scores and narrative engagement scale. So people who were who self-report better perceptual ability actually report less narrative engagement, which is really interesting to me because it tells us that there are so many different ways of listening to music. Right? I started as a very classical violinist, and I kind of pride myself for perceptual ability and fine-grained differences in pitch. But maybe that just means I'm missing out on these remarkable associations that other people are hearing when they're confronted even with very unfamiliar music. So far, I think I've convinced you that predictive coding taps into the reward system, and that musical anhedonia seems to be an abnormality in the mapping between prediction and reward. And these predictions come from statistical exposure to sounds, and they can operate over spectral as well as temporal domains. And that cultural differences, they don't seem to change how you form familiarity and liking, but they do seem to come from real-world associations that then are mapped onto musical predictions and imagination. Right, so I wanted to turn in my last remaining 2 minutes, 7 minutes, great. Then I have a lot of time to talk about the more applied stuff and music-based interventions. So in the lab, we've developed a task, music listening functional MRI task, where people can come in, and we have young adults and older adults do this, listening to music of either that we select for them or that they select for themselves, some of which is well known and some of which is unfamiliar, including the Bullen-Pierce scale melodies that you heard about before. And they just had to make ratings for how much they liked and how familiar they were with each excerpt. Right? So this is a task that we've used in many different instances in the lab, and it's quite a large database that we can mine now. And my former student, Alex Belden, showed that regardless of how much you like a piece of music, it engages your auditory system, which is not surprising. But then when you're listening to music that you love, additionally, you engage areas in the reward system, specifically including the medial prefrontal cortex and also subcortical regions, including the hippocampus. And so he then also did auditory seated resting state functional connectivity, right? Taking areas in the auditory network that was defined by a previous student using an atlas, and compared the functional connectivity of the auditory seat regions towards anywhere else in the brain, both at rest when doing nothing, and also during music listening. And he did this for both young adults and older adults. And so what we saw when during resting state was that there was auditory areas were more connected to auditory regions in young adults than in older adults. But then in music listening, what we saw was that the auditory regions were more connected to the medial prefrontal cortex, which of course is a classic node of the reward network in young adults than in older adults. Right? So there's something about the way music seems to engage functional connectivity between the auditory system and the reward system that seems to decrease with age. So this is something that I think has a lot of implications for music-based interventions as we start to develop them. We've kind of started to dip our toes into music-based interventions by working with music therapists from the greater Boston area, mainly Suzanne Hanser, who started the music therapy department at Berklee College of Music, and her students. And we also work with neurologists. Maya Geddes she's now at McGill, but when we started this project, she was at Harvard Medical School. And we worked together to develop this 8-week mindful receptive music-based intervention where older adults were asked to listen to music for an hour a day, quite consistently and quite mindfully, and note any feelings that they had or feelings and sensations in their bodies during music listening by writing about it in a logbook. And before and after that 8-week intervention, we had MRI, and we also did neuropsychological testing. So this is something that I think will be a useful paradigm to borrow for many different studies on music-based interventions in the future. But so I'll just show you the tip of this large data collection iceberg right now. And so what Milena Quinci and Alex Belden and my lab members that did was look at changes in auditory reward connectivity before and after intervention. And so when we seeded the auditory network, which I'd shown you 2 slides before, this is the auditory network, and we searched for voxels anywhere in the brain that increased in its functional connectivity after intervention compared to before intervention. And the only voxels that showed up was in the medial prefrontal cortex, which is of course part of the reward system. And so we also saw that to be sensitive to self-selection, right? So this increase in auditory reward connectivity, that specific cluster, was specifically even more sensitive for self-selected music listening compared to other selected music listening. So there's something about the auditory engagement of the reward system that changes throughout the lifespan, but is enhanced by mindful music-based listening interventions. All right, so that's something that taps explicitly into the reward system. We also have heard many examples and work throughout the day about how music also taps into the movement system, right? So, and groove is a really perfect example of that. So my former student, Anna Kroedinger, also had worked on dance for PD as part of her thesis, which of course has many different sites around the world. She was amazing. She she brought her little lab that included computers and finger tapping gear and headphones. She went into many different sites around the US, and she tested these Parkinsonian patients and also controls for Parkinsonian symptoms using the UPDRS scale. And she saw that there was a significant reduction in Parkinsonian symptoms after 4 months of dance intervention in the Dance for PD program. And then we wanted to specifically pick apart rhythm as a mechanism, or groove as a mechanism for this improvement. And so what she had people do was tap. I'm not going to ask you guys to do that. Tap in time to different pieces of music that were either high groove or low groove. Right, so Superstition, for example, is one of the highest groove music of all time. And so people were very consistent in tapping to that. However, this is one person's data. What we saw was that after 4 months of dance intervention, this Parkinsonian patient actually decreased in their entropy of inter-tap interval, especially for the low groove pieces of music. And furthermore, this entropy was predictive of improvement from the Dance for PD program as measured using the UPDRS. So that's really quite exciting. And I think that I will just use this as an opportunity to kind of relate back to this overall model of how music can bring us together, but hopefully kind of transcending this kind of pure theoretical debate, we could actually use this knowledge to design some music-based interventions for healthy aging, for people with Parkinson's disease, and also we're running trials now on Alzheimer's disease. So I think I'll stop there and thank you guys and thank all the funding sources. And I'll also say that all this work requires lots of interdisciplinary working with together, working with other researchers in the field and in different fields. We've recently published an edited volume. A few of you are authors on that volume. Thank you. It's called The Science Music Borderlands, that really encourages a dialogue between humanistic and scientific approaches to music. So that just came out in MIT Press. You don't have to buy it because you can go, it's fully available online, open access, but there are some really wonderful folks that have contributed ideas to that. So thank you very much. Thank you.
Thank you, Psyche. So we've got some time for questions. Peter in the back. Maybe just, shout it out.
Is there anything, I mean, you
Okay. I'll repeat it.
Is there anything like that in rhythm? Do you think of anything like that in rhythm?
I'll just repeat the question. Can you repeat the question?
Is there anything akin to the Bohlen-Pierce scale in rhythm? I mean, I think it starts out with something that's unfamiliar, but still obeys some acoustic principles that you might expect to be familiar. Yeah, so I guess it reminds me of like an old discussion we had actually with some people in the room, looking at shepherd tones and how like the classic shepherd tone is a pitch-based tone, but you can actually make a rhythm-based shepherd tone. So I guess something like that. I'd have to think a bit more about it, but that would be a place I would start thinking. Christina, hi.
Hi, wonderful talk. I was curious about when you were doing the timbre study, which is really cool. I remember on Twitter, I think you said this is like everything is all related when you were talking about it, and that is what it feels like. But so you said that you kind of partialed out the melody learning, but I was curious if you could talk a little bit about like you talk about a chord is kind of a major chord or a minor chord because it still has these kind of more simple integer ratios. So could you predict that some of the kind of pre-stuff was also just because of the integer relatedness? Like I'm thinking of consonance and dissonance. So not at all from the melody that they heard before, or maybe a bit from the melody they heard before, but the probe tone is all by itself. But if it had been an accord with like the root and that note, could you have found a similar probe tone profile for the Bohlen-Pierce?
Yeah, I mean, I do think that there are some constraints to the Bohlen-Pierce scale that made it especially easy to learn, and so those probably do have something to do with harmonics and the congruence and how the scales afford certain chords, and so I think people might be sensitive to that. I've tried to test many years ago a version where we squished the Bohlen-Pierce scale into an octave and played it, and it turns out people actually still learn it. But I didn't try to see whether that then interacted with timbre, but that would be an interesting future project. Yeah.
Hi, that was a super interesting talk, and I love the interdisciplinary work. And I have a very similar question, and apologies if maybe you covered this in the talk, but I was wondering if you also explored some of those sort of like in a harmonic context as well, where you have multiple notes from the Bohlen-Pierce scale sounding at the same time. I'm not sure then again, I'm also not sure if with such a novel scale, if there is like, if we would be familiar with what like a chord would sound like or how the sort of harmonic system would work.
Yeah, that's a great question. So there are, so I haven't actually, so I guess this chord progression, I think most people hear that as chord progression rather than as 4 separate tones that just happen to have different harmonics. And that is something that I used in the ERP study a long time ago, which I think I have a slide for here, where we showed that if you take groups of chord progressions that and played them in the Bohlen-Pierce scale and played them with either high probability or low probability, people start to show an ERAN-like waveform in the event-related potentials within about 20 minutes of listening to these chord progressions. So yeah, so it has been done. And I think that the small avant-garde composer community that makes this also have, I think it resonates with what they found as well.
Great, thank you so
Does
much.
that answer the question?
Yes, yeah, it does.
Yeah, it was a very fascinating talk. I just had a two-part questions. So for one of the slides, you mentioned that there is differences between anhedonics, hedonics, and hyperhedonics in terms of familiarity, where at some point anhedonics just completely give up. So I'm wondering if that's also the case in general for people for songs they just dislike. And I guess if you're able to actually teach people or train them to like music, if that changes their reward, or if you're able to actually use some interventions to increase reward and familiarity.
Fascinating. Yeah, so I think, so in the way we're defining musical anhedonia here, which is the tertile split, it's really just one way of splitting a continuum of folks, right? And so I think it's very similar to another result that I show later, where the preference for complexity scales with individual differences in music reward sensitivity. So I think we all have different curves, a bit like this, maybe that operates differently on different features of music, right? So there are some pieces of music that I can listen for over and over again, and there are some that I just hear once and I'm like, done. So I think there's a lot more work that can be done there. And I will say, right, is there a way to intervene on this reward sensitivity? And I think that's exactly what our mindful music listening intervention was doing. And I think to some extent, maybe some kinds of music training are a little bit doing that anyway. And then there's also a third really wild finding. We had, not really a finding yet, but our colleague and friend Shinya Fuji, who was we last hung out with in ICMPC in Tokyo, they think that you can do neurodoping, right? And that's a little bit related to the Satori Lab's finding a couple of years ago of up and down regulating the reward system using transcranial magnetic stimulation, right? So they would like to do that with like other kinds of stimulation. I think that's wild, but it might be. It's not impossible.
Thank you.
We have one online question.
Sure. So we have one from Mehmet Verkak. So regarding some of the Boston versus Beijing observations, could the difference or differences be due to the newly invented structure of the BP scale harmony being based on numerical ideas that came from Western tonality in the first place?
Right. So that's one question that we had, but we the scale we had people we had a pre-listening task and both people from the Chinese group and the Boston group both rated the Bohlen-Pierce scale clips as being unfamiliar and similarly unfamiliar. Right. So, but it's true that maybe both groups had some experience with Western music, and there maybe were some similarities between how the Bohlen-Pierce scale was conceived and some Western tonal ideas. But I think it is still one major step along the direction of becoming less familiar and less kind of entrenched in a culture. Hope that answers the question. Thank you, Mehmet.
Thank you so much, Psyche. Let's thank Psyche one more time.
Thank you.